When two similar waves meet, they interfere. The principle of superposition tells us that the result of such interference is just the sum of both waves. So if we have two identical waves that are in phase with each other, the result is a similar wave with a larger amplitude, the sum of these two. If we have two identical waves that are completely out of phase with each other, the result is 0, because positive plus negative, 0, 0 plus 0, 0, negative plus positive, 0, it's zeros the whole way across when you sum them together. And if we have two waves that are just a little bit out of phase with each other, the result is a wave that has a similar frequency, but is a little out of phase with either of the other ones. It's somewhere in between the extra large wave and the extra zero wave. You'll notice that if both waves have the same frequency, the only difference is how out of phase they are. In the case of these, I only moved this bottom wave over. So we can adjust the output just by moving this bottom wave back and forth. And we have an example of that with our next demonstration. The Michelson interferometer. The easiest way to generate multiple light waves that have the same frequency and are in phase with each other is using a laser. So we use a laser to shoot out light waves. A beam splitter takes half of the waves and bounces them in one path, and half of the waves and bounces them in another path. A mirror on each path bounces the light waves back, they hit the splitter, and then continue down to the screen where we see them. Now we know that the waves start in phase with each other, so they're in phase with each other when they hit the beam splitter. If they go the same distance on each leg, then the waves will still be in phase when they recombine, and they'll be in phase when they get down here. The result will be an extra bright patch. But if we slide this mirror back just a little bit, say half of a wavelength, then one of the light beams is going to be half a wavelength out of phase when it gets here. And if it's half a wavelength out of phase, the result will be 0, a dark patch. And of course, if it's anywhere in between, we will get something between bright and dark. Here we have a laser that shines into the interferometer apparatus. It hits the beam splitter here. Half the light's going to bounce to this mirror and back. Half the light is going to bounce to this mirror and back. And then the light's going to shine out that way. Using this knob down here, we can move this mirror back and forth. And here is the resulting interference pattern. Green light has a very small wavelength, around 540 nanometers, so any minor bump can change the length of one of the paths. But this is what happens whenever I move one of the mirrors.